Thank you. Well, to begin with, I want to thank the organizers for having a conference in such a beautiful place. I think it's by far the best conference place I've ever been to, so thank you very much. And I think this really raises the bar for the organizers of the next conference. So people in Granada, now, there is a standard to keep up with. So I'm talking about something that I talked about already. Some of you already saw it once, some even twice. I tried to reshape the talk a little bit, but there are going to be repetitions, so I apologize for that. This is a joint work with Carlo De Bernardi and Jacopo Somaglia, both in Italians and in Italy. And I will start with a question from Ruben Medina at the Winter School in Abstract Analysis, I think in 24, but I'm not 100% sure. And Ruben came, the Tuesday/Wednesday evening problem session. He asked whether if you have a Banach space, possibly infinite dimensional, can you find a net which is closed under addition? So if you have two vectors in the net, the sum of them is also a vector of the net. Just to be on the safe side, what is a net? Well, first I have to define what is an R-separated set, which is R-separated. The distances are at least R, not a big surprise. R-dense means that for every point in your space, there is one of the elements in your discretization set D which is close enough. And a net is both of them together. So it is a collection of points in the space which is close enough to every point but doesn't cluster to itself. So for example, if you take in the plane the integer grid, this is a net because the distances are 2 and it should be square root of 2 divided by 2 separated, probably, something like this. So this is a classical, this most simple example you can think of. Now, why should Ruben come up with this question? Well, I don't know, ask him, not me. Here is a possible answer. There are papers about Lipschitz free spaces. We know of them, of many of them. There is a certain search in looking for Schauder bases in Lipschitz free spaces. In particular, I think the first paper was by Eva Pernetska and Petr Hayek, where they build a Schauder basis in the Lipschitz free space over the finite dimensional L1 and in some other spaces. And later, Petr and Ruben have some other constructions. Sorry, I said it wrong. In the net, in the grid over the finite, over blah blah blah. And Ruben and Petr have some other papers where they show that the free space over a net has a Schauder basis for some net in some Banach spaces. For example, script L infinity, grid in C0, and so on. So for some well-behaved Banach spaces and some well-behaved net, you can build a Schauder basis on the free space over the net. And remember that there is this problem by Carlton whether the free space over a uniformly discrete metric space has the bounded approximation property, which is weaker than a Schauder basis. So there is some connection to some famous problem by Carlton. However, in these results, it kind of helps that you don't have a net, but you have a grid. So like something like the integer lattice. So if you have a net which is closed under addition, it is kind of closer to a grid. You can sum vectors and you have a bit more control on how to project from the bigger piece of the net to the smaller one. So, I mean, this is something that Ruben said in this question. It might help to construct Schauder bases by retracting bigger blocks of the net to smaller ones. So, heuristically, this means that you can discretize your Banach space because a net is a discretization. Sandra was saying if you look far away, the net is a Banach space, nothing changes. If you are far away, they are the same thing. It's a discretization. And it's not only discretization in the metric sense, but also in the algebraic sense, because it still keeps some algebraic structure. So this seems like something reasonable. However, not every open problem asked there is an open problem, because just after Ruben asked it, Michael Douka pointed out that this was known. So if you are in the separable case, there is a result by Dilworth, Odell, Schlumpert, and Jacques, where you can get a subgroup. So not only closer under addition, but really a subgroup. And you can get optimal, well, not optimal necessarily, but like quite good estimates on the number. So it is one separated and one plus epsilon dense. So the 2 points have a distance 1, but every point is a distance 1 plus epsilon from some of your elements of the discretization. And later on, I emailed Michal asking for the reference to this paper because Michal just said, well, there is this paper, and I didn't know. And I asked him, and I did not specify separable. So Michal sent me the paper, said, like, for the separable case, it's in this paper here, theorem 5.2 maybe. In the end, when he wrote me, what about non-separable X? And we digged a little bit more, and it turned out that this is also not an open problem, because even before Rogers had a proof that in every Banach space you can get one separated, and instead of 1 plus epsilon you get some annoying fraction. I have to say I don't have this paper. I have the Matzenet review, and this is what is claimed there. I don't know whether the reviewer of Matzenet forgot to write separable. So I don't know whether this result really is true. I am looking for the paper, but I still don't have it. So probably this is what he proved, but I'm not 100% sure. I'm making no promises here. What I know is that in a slightly more recent paper, there is a question whether you can get rid of the fraction, because we don't like fractions. And the answer is yes. This maybe was an open problem. I don't know. Maybe this is also published, but I don't know. Anyway, this is one thing that we know how to do. We can build in every infinite dimensional Banach space one separated and 1 plus epsilon dense subgroup. And now the main question is, who cares? Like, you can do it, you can get rid of a fraction and get a 1, but this is not something that you go to a conference to talk about. So is there any motivation? The answer is yes. The truth is that we were doing something else, and at some point we realized that, but if I look at the proof, I can simplify to get it this argument. So, as I said, I was trying to not give the same talk, so I just rearranged a little bit, but now I will go back to the real motivation that we had. However, one thing I want to say is that our construction is, I don't know if simpler than Rogers because I cannot access his paper, but our construction is really elementary. You enumerate a dense family in X, and then by induction you add vectors and vectors in order to approximate every of your elements of your enumeration. So it's really an elementary inductive argument, only using Ray's lemma to find the next guy. So what I'm saying is, if you want to get a subgroup with some additional structure, you can probably fine-tune the argument, putting in your conditions into the argument to get something that you like. So what I'm saying is the construction is flexible. It might be useful. It's maybe not such a beautiful result, but it might be something useful. It might be that you can fine-tune your argument to get what you want. For example, if I take a Hilbert space, instead of using Ray's lemma, I have a stronger version, which is called perpendicularity. And in particular, in a Hilbert space, I can get, instead of 1 here, I can get square root of 2. Because if I use orthogonality, automatically things are square root of 2 separated by Pythagoras' theorem. If I play a little bit smarter, I can even get rid of the epsilon. Here, I never said it, but of course, epsilon is positive. Like, epsilon is positive everywhere but in the bathroom. In order to blackboards in the bathroom, there was written epsilon less than 0. Besides this, epsilon is always positive. So here there was 1 plus epsilon. Here you get 1 dense and square root of 2 separated. Now, these two values, the fact that you get exactly these two values makes a lot of sense. And now I want to explain how this is of any relevance. So now we'll talk about the real motivation we had why to study these things. So suppose that you have this separated and dense set. So you have this some set of points. They should be like a subgroup. So I'm trying to make them more or less regular. What I can do is I can consider the so-called Voronoi cells. What does Voronoi cell mean? Well, you can imagine that you live in Vienna and you have a good list of your favorite restaurants. So when you go around with some of your friends or some people are visiting you, at some point you want to go for dinner and depending on where you are in the part of the city, you might say, okay, nearby there is this beautiful restaurant, let's go there. So what you do is you have a discretization of the map of the city in which you partition the city by regions in which in each region you know that your favorite restaurant, which of your favorite restaurants is in the region. So for example, if I have these points, maybe I will change color, I know that if I am here, my favorite restaurant is this one. If I am here, my favorite restaurant is this one, and so on. So you partition a domain by saying the points that are closest to something. So if, for example, if I have these 2 points, this region will be closer to this one, then it's going to be something like this, right? I want to be closer to this than to this, so I'm going to be in this half, and so on. These are called Voronoi cells. And you can define them in a mathematical way. So if you have a sum set D, the Voronoi cell, and you take a point D in D, is all points in X, such that the distance from X to D is smaller than the distance from X to H for every other H. The points for which D is the closest restaurant, right? Now, if I am in a Hilbert space, what does it mean that, I have to change board. I have these 2 points. What does it mean that I'm closer to this point than to that point? Well, I'm in a Hilbert space, so I can draw the segment. This I can do every time. But in a Hilbert space, I can take the perpendicular hyperplane. So I take the hyperplane, the perpendicular one, and now I am closer to this point than to this point if and only if I'm in this half space, right? Of course, because if I project down, I have to be in this half segment. So the Voronoi cell is an intersection, of course. It's the intersection of all these half spaces. Well, but this guy is convex. So the Voronoi cells in a Hilbert space are convex. And now, if my set is not a set but is a group, the Voronoi cells, so the set is invariant under translations. So if I move my set, nothing changes. But then the cells must not change. So what I obtain is that the Voronoi cells are all translates of the same object. So there is a guy here, and all the Voronoi cells are translates of the same guy. And what did I prove? Well, that there is one line missing. This guy is a body. It's a convex set. It's symmetric because, of course, like there is a point and its opposite. It's bounded because it must be bounded. It cannot go to infinity because these guys are dense. And it's a neighborhood of 0. So it's the unit ball of an equivalent norm. So if I change norm and I use this guy as a unit ball, I tile the Hilbert space by translates of this guy. So what I obtain is there is a reflexive Banach space that can be tiled by translating a single set. You take a set and you move it around until you tile everything. Now this looks familiar because if you look on the ground, you are tiling the plane by squares, right? So this could have been done. Well, okay, should have written infinite dimensional. You can tile C0 by balls, take the square and move it around, you tile C0. There is a construction by Klee in which you can tile L1 by translates of the unit ball, but none of them is reflexive, while L2 is. And given these 2 examples, Fomf and Lindenstrauss were asking if it's possible to tile a reflexive space by translates of a single body. This is some paper whose title I actually don't remember, but then in their handbook article, there is some comment about a problem similar to this, and then the same problem is also repeated in the yellow book with open problems. And the truth is that we were trying to do this because originally we thought it was not possible to tile Hilbert spaces with balls. We found out it was possible. After we found out it was possible, we found out this problem. We really didn't know it. And after we found out this problem, we realized that we also get this subgroup in every Banach space. So this is the history of how the things really went. And now, what happens if instead of L2 I take LP? Nothing changes. I still have disjointly supported vectors, which give me, instead of square root of 2, 2 to the 1 over p. No one is surprised here. So in LP gamma, I get 2 to the 1 over p separated in one dense. Nothing changes. What does change is that I don't have orthogonality. So I don't know that this body is convex. So what might happen is that the body that is not convex. It is always star-shaped because there is a center. It is star-shaped. So what might happen is that this set looks like something which is very familiar to the people of this conference, because in my understanding, it looks like this a little bit. And this picture, I didn't steal it from the webpage of the conference. I went there to take the photo. You took it from the internet too, okay. So the thing why it only works in L2 for us is really convexity of the Voronoi cells. And in the other LPs, what we get is some object like this. And I'm a bit early, but I had 2 minutes left already, so I will finish here. Thank you very much. I'm not sure, because we have to start listing with an enumeration of all the vectors, or at least of a dense sequence. Maybe if can you enumerate explicitly the finitely supported rational sequences? I mean, it is easy, but you really need to list a dense sequence. Once you have a listing, it is, but you have to list them. So if you can list, I can do it. If you can't list, I can't do it. So it's basically up to you somehow. So I'm useless, I'm sorry. We don't know. Well, the best it's known in the separable case is the result by price, that you can tile by bodies that are, well, you know. It's still hopeless, yes. It's really unclear. We didn't try to, I don't understand Klee's argument Price argument well enough to be able to say whether you can combine the two things. It might be that if you understand very well his argument and ours, you can glue them together. But originally Carlo thought that it was impossible in any Hilbert space. So we were very surprised to get it in some non-separable ones. Getting it into a separable case would be really surprising. And we would have to be smarter than Price. Which is not the most likely thing, right? But it's something that we didn't explicitly try, but at some point somebody should try to do. At least to make sure that it doesn't work as easily as just gluing together the two things. But yeah, I don't know anything more than the result by Price, essentially. Yes. Yes, this is something that, well, in this case, it has as many generators as the density character. And it is, I mean, our construction has you can explicitly see that it is free because we construct generators after one another. In general, for countable, it's easy to see that they are all free. In the non-separable, there is a recent preprint by Tomek Kania and Jamovit Kostana, where they prove that it's free in general. Every discrete group in a Banach space is free abelian. I tried to read the paper, but I they use elementary submodels and some singular compactness theorem by Shelah. It's beyond me. I actually was trying for a little to give a direct proof of their argument, but I don't understand their proof well enough. But there is a paper by them, so you're right. Every discrete is free. And this is something I actually wanted to say, but I forgot, so thanks for the question.